let's look at some tricky integrals that use the substitution rule. So these are ones that are going to require a little bit of extra manipulation in order to figure them out. So let's look at this first one. This is the integral of dx over e to the negative x plus e to the x. So just taking a look at this, you might say, okay, well maybe I could try saying u equals e to the x. And then you have du equals e to the x dx, and that doesn't seem to really get you anywhere because we don't have an e to the x dx anywhere. So maybe I can kind of create one. So what I can do is maybe say, well, let's write this as the integral of, and it would be nice to do something here to get an e to the x up top. Well, I have an e to the negative x right here, and I know that e to the negative x times e to the positive x, well, that's just 1. So I wonder if I can maybe use that to my advantage. Maybe I could multiply everything by e to the x. So if I do that, this will become a 1 down here, and then I will have e to the x times e to the x. That's e to the x squared, if I want to write it like that. And then on top, I have e to the x, and I'm going to bring the dx outside now. Remember that e to the x squared, that's the same thing as e to the 2x, so you could also write it like that. But now I think I can do a u-substitution. In fact, I can do this u-substitution that I have right here. And let's see, what will that turn into? So if I do that, then I have the integral of 1 plus e to the x squared. So that's going to be u squared. And then I have my e to the x dx on top. That's just du. And this is great. This is an integral I know how to do. So this one, if you remember, is an inverse tangent. So this is the inverse tangent of u. Some people write this as arctan plus a constant. So remember, the derivative of the inverse tangent is 1 over 1 plus x squared. So I want to write this in terms of x. So I can write this as the inverse tangent of, and instead of u, I'm going to rewrite it as e to the x plus c. And I'll leave it to you to check this if you take the derivative. It's pretty easy. You take the derivative of inverse tan, that's 1 over 1 plus, and in this case, e to the x squared times e to the x on top, and then that looks like this, and then that, of course, we discovered was the same thing as the original integral. Okay, so that one was not terribly tricky, but let's keep going. We'll find something that's even trickier. Okay, how about the integral of x cubed times the square root of x squared plus 5 dx? This one is a little trickier. Let's see what we could possibly do here. So usually when you see a square root, you think, okay, well, I'm going to let u be the thing under the square root, and if you did that, you would get du, in this case, being 2x dx. And that's a problem because, well, I don't have x. I have x cubed here. So I need to think of another way around this. Well, remember that x cubed is really the same thing as x squared times x. And I do have right here, I have x dx, and that's du over 2. And I have, if I solve this for x squared, I have x squared being equal to u minus 5. So I think I can actually, believe it or not, rewrite this using u. And so let's see how that might be. So first, I'm going to use this idea. X cubed is x squared times x. And I'm going to rewrite this x cubed out front. So I'm going to put the x squared first, and then I have an x squared plus 5 under here. And then I'm going to move that other x over here, so I have the x dx. Now I think you can see how this is going to work. So I have an x squared out front. That's going to be u minus 5. Then I have the square root of x squared plus 5. That's the square root of u. That goes there. And then I have x dx. Well, x dx, if we look at this, is just du over 2. And that now is an integral I know how to do. So let me kind of rewrite it in a better way here. This u square rooted, that's u to the 1/2. So this is u minus 5, u to the 1/2, and then I have du over 2. Well, that over 2 can come outside, so this is 1/2 times the integral of, and now I have u to the 1/2 times u. Well, u to the 1/2 times u, that's going to be u to the 3/2. And then I have minus 5 u to the 1/2 du. And this is, like I said, is an integral that is pretty easy. It just uses some fractional exponents here. So this is going to be 1/2 times, okay, and then this is going to be u to the 5/2 divided by 5/2, but I'm going to rewrite it as 2/5 u to the 5/2. Remember, this is just u to the 5/2 all divided by 5/2, but dividing by 5/2 is the same thing as multiplying by 2/5. Dividing by a fraction is the same thing as multiplying by the reciprocal. Minus 5 times, and this is going to be u to the 3/2 divided by 3/2, or 2/3 u to the 3/2, plus a constant. And let's see, let's simplify this a little bit. So if I distribute the 1/2, these 2's are going to cancel on top. So I'm going to get 1/5 u to the 5/2 minus 5/3 u to the 3/2 plus a constant. And finally, I can plug back in for u. U was x squared plus 5. So this is going to be 1/5 x squared plus 5 to the 5/2 minus 5/3 x squared plus 5 to the 3/2 plus a constant. Okay, so let's kind of review what happened here. So I did the initial trick of letting the x squared plus 5 be u, because that's normally what you do. You would like to have the square root of u. That makes things a little bit easier. And I realized I couldn't quite do it because then I had du being 2x dx. But if you remember x cubed, you can kind of factor it as x squared times x. And if you rewrite the initial step here, this substitution solving for x and plugging back in, sometimes that works. And this is a trick that works a lot of the times when you have integrals involving square roots. So if you have a u-substitution integral, has a square root in it, and you can't seem to get it to work, try a trick like this. This is something that works great with square roots. Okay, the next integral I want to look at is the integral of dx over x squared plus 4x plus 13. And initially, there's not a heck of a lot to do. I mean, we could say that u equals x squared plus 4x plus 13, but that's not going to help because the derivative 2x plus 4 does not appear anywhere else in the integral. So my advice here when you have something that looks like this is to complete the square. So let's recall how that works. So if I have x squared plus 4x plus 13, what I want to do is I want to add something here and then subtract it again. So subtract the same thing here such that this thing factors as a perfect square. And if you remember, the way you do that is you take the thing in front of the x, this 4 here, divide it in half, that'd be 2, and square it, that'd be 4 again. So what I'm going to do is I'm going to add 4 and then subtract 4. Now this thing here, as a perfect square, looks like to be x plus 2 squared. And then 13 minus 4, that's going to be 9. And so I can rewrite this integral as the integral of, and then in the denominator, x plus 2 squared plus 9. And that's completing the square. So what? Why did I want to do that? Well, now let's try a u substitution, and we will let u be x plus 2. How does that work? Well, let's try it and see what happens. So then du is just dx. Well, if I did that, I'm going to get u squared plus 9 on the bottom. Well, I know that the integral of dx over 1 plus x squared, that is the inverse tangent. We saw that earlier, so inverse tangent of x. So that's what I kind of want to look for. Right now I would have u squared plus 9. I would like to have u squared plus 1. So maybe before I do this, let's rewrite this a little bit. So I want to make this a 1, so I'm going to kind of multiply top and bottom by 1/9. So if I were to do that, I would get 1/9 times x plus 2 squared. So let's do that here. And this now will be a 1, which is good, that's what I wanted. And then up top I have a 1/9, multiplying everything by 1/9. Okay, now this thing right here, this 9 is really 3 squared, so I could kind of bring it inside the square if I want. And this 1/9 up top can come outside, so it's a 1/9 outside, the integral of, and this is really x plus 2 over 3 all squared, plus 1, and then I have dx. So I can see that maybe instead of letting u be x plus 2, maybe a better choice would be to let u be x plus 2 over 3. And so now du is 1/3 dx. Great. Now this is going to look like I want it to look here. So let's continue way over here. So this integral equals, I have the 1/9 outside, and the integral of, and now I have x plus 2 over 3, that's all u. So this is u squared plus 1. Up top I have a dx. dx is 3 du. If I rewrite this here, 3 du is going to be my dx. So this is 3 du. That 3 can come outside and make that a 1/3. And I have the integral of du over u squared plus 1. That's this integral right here. So this is the inverse tangent of u. And then I have my constant. And of course we want to rewrite this not with a u but with an x. So this is the inverse tangent of, and u was this thing, x plus 2 over 3. And that now has a constant added to it, and that's my answer. Okay, so now let's try the integral of dx over e to the x plus 1. So again, I have that problem where if I do my u being u equals e to the x, I have that problem where the du being e to the x dx doesn't appear anywhere else in the integral. I need to have an e to the x up here. Now last time I did that by multiplying top and bottom by e to the x, but I can't do that here because that's not going to help me get something on the bottom that's something I know how to integrate. So instead I'm going to be a little bit sneaky here. I'm going to write this integral as, and I would love to have an e to the x up here. So instead what I'm going to do is write this as e to the x plus, and then I have to be a little bit sneaky here how I'm going to do this. I'm going to write e to the x plus 1 minus e to the x. And then e to the x plus 1 on the bottom, and dx. Okay, so why is that? Well, remember that this is really 1 times dx, so there's really a 1 up here. So there's my 1. And then I'm just taking e to the x and subtracting it again. So I didn't really do anything. I kind of like added 0, I guess, to the top. But now look what happens. So I can rewrite this as, if I break this into 2 different fractions, I have e to the x plus 1 as my first part, over e to the x plus 1 minus e to the x over e to the x plus 1. And all of this whole thing dx. This is just 1. I know how to integrate that. And this now will have an e to the x dx on top, which is great for using this u substitution. So this is really the integral of dx minus the integral of e to the x over e to the x plus 1 dx. Great. So now this first integral here, that's easy, that's just going to be x minus, and now this integral here, I can use this substitution. So let's do that. So I have on the bottom, I have u plus 1, and on top I have du. Okay. Well, it might be nice to not have the u plus 1. It would be nice to just have a u on the bottom here. So maybe what I could do instead of doing this substitution right here, maybe I could modify it a little bit, because what if I just did u equaling e to the x plus 1 instead, and then du would still be e to the x dx, right, because the derivative of 1 is 0. So let's actually do that. So if I were to do that instead, so I still get the x there, and then this would be, so the bottom would be u, and I still have du on top. And that's a very easy integral, something I know how to do. So it's going to be x minus, this is the integral of the natural log of u. And I have to tack on a constant. And of course I don't want to have it in terms of u, I want to have it in terms of x. So u is e to the x plus 1. And then I have my constant. And e to the x plus 1 actually is always going to be a positive number, so I really don't need the absolute value sign here. I can just rewrite this as the natural log of e to the x plus 1 without the absolute values. And that's my final answer. So this is a very sneaky integral to do using a u-substitution. If you notice, it's not obvious to add e to the x and subtract e to the x, but remember how I figured that out. I did what I thought would be a normal u-substitution, setting u equaling e to the x, and then I thought, okay, well, I need e to the x dx on top. Is there any way I can get that? And I can by writing e to the x and then subtracting it again. And then I went from there. So you have to try different things out when you're trying these sneaky integrals here. Let's look at one more. Okay, here's the last integral I want to look at, and this is the integral of tangent cubed x dx. Okay, so where to start? Well, there's not much to start with here, I guess. Start with the u-substitution u equals tangent of x, because, well, there's not much else to do. And remember that this integral here, this is really tangent of x cubed dx is the same thing. It's just notation. Instead of writing the parentheses in the cube, people write the 3 right here, but it means tangent, that whole thing cubed. So if that's u, then du is, you have to remember your trig derivatives. The derivative of tangent is secant squared. So this is secant squared x dx. Great. Well, let's see. Do I have a secant squared in here? I do not. So I have to kind of figure out what to do here. Well, so this would be, if I wanted to kind of rewrite this a little bit, the dx here is du over secant squared x, all right. And what's secant squared? Well, remember that from the Pythagorean identity, sine squared of x plus cosine squared of x equals 1. And if I divide everything here by cosine squared, then sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1, and 1 over cosine squared is secant squared. So I see that this is really tangent squared plus 1 on the bottom. And that's actually a good thing, because I have tangent in terms of u. Remember, tangent is u. So this is just u squared plus 1 on the bottom. Aha. So let's try that. If we plug that in, what do we get? Okay, so first I have tangent of x cubed. Well, that's just going to be u cubed. So that's u cubed. And then my dx, remember, is du over u squared plus 1. Okay, so let's kind of rewrite that a little bit nicer here. I have u cubed on top, and I have u squared plus 1 on the bottom, and then I have du. Okay, still not an integral I know how to do, but it's getting a lot closer here. So now I think what I'll do is another u-substitution. So if I wanted to do another u-substitution, how could I do this? Well, let's use a different letter. How about v? And I'll say that v is, let's try u squared plus 1. We'll do the thing on the bottom there. So the dv is 2u du. Well, I have u cubed du. Does that help me at all? Let's think about this. Well, remember that u squared is v minus 1. We saw this trick before, kind of doing the substitution and then solving for the other variable here. So u squared is v minus 1, and u cubed, remember, is u times u squared. So if I rewrite this just a little bit here, I have u squared plus 1 on the bottom, and then I'm going to rewrite this as u squared and then times, and then I have a u du. And u du, if I look at this right here, is 1/2 dv. Alright, so let's plug all this in here. So this is the integral of So u squared is v minus 1. U du is 1/2 dv. And then on the bottom, I have u squared plus 1. That's just plain old v. And I think this is an integral that I know how to do. So let's kind of make some room here. And so next line down, we'll start over here. This is going to equal the integral of, and so this is a 1/2 that can come outside actually. So let's put that 1/2 out front. And then I have a v minus 1 over v. V minus 1 over v, and then dv. And let's break this up. So I still have the 1/2 there, and this is the integral of v over v is 1 minus 1 over v dv, and this I can do. So this is going to be 1/2 times the integral of 1, that's v, and the integral of 1 over v, if I remember, is natural log of v. Great, okay, and then I have a plus c. Now I have to do a lot of plugging back in, so from here on out it's just kind of working backwards. The v, remember, was u squared plus 1, so this is a u squared plus 1. And then I have minus the natural log of u squared plus 1, great, plus a constant. Okay, now we'll keep going because I don't want u squared plus 1, but I want it in terms of x. And remember, u is tangent of x. So this is 1/2 times, and then I have tangent of x squared. So this is tan squared of x here, plus 1 minus the natural log of, and then again, tan squared x plus 1. All this plus a constant. Now tan squared plus 1, remember, is secant squared. So if I want to be real fancy, I can rewrite this as 1/2 secant squared x minus the natural log of secant squared x. Okay, plus a constant. And let's distribute the 1/2. So this is 1/2 secant squared x minus 1/2 natural log of secant squared x plus c. And this 1/2, if you remember your log rules, you can bring that 1/2 up as an exponent. So let's rewrite this again as 1/2 secant squared x, and this is, let's see, secant, remember, also is 1 over cosine. So secant squared is 1 over cosine squared. And this minus 1/2 is going to become an exponent. So I'm going to do both of those things right now. So this is going to be plus natural log of, and then I have 1 over cosine squared x, and this is to the negative 1/2 plus c. Well, cosine squared, and then I have, this is really a square root, and it's minus, so that's going to flip it. So I think, there's a lot of algebra here, but I think if this ends up working, this is 1/2 secant squared x, and then that ends up flipping the cosine and square rooting it, so this becomes a natural log of just a plain old cosine of x. And then I have my constant. So that integral was pretty messy. This is a very tricky integral. It had several different things in it that were not obvious. But again, you saw some of these things before. Remember the thing where we did the u cubed and we broke that up as u squared times u. So that idea of factoring often helps. And then rewriting the expression for v here, we rewrote the u squared in terms of v and plugged it back in. So these little things do come up now and again. But yeah, these are pretty tricky integrals. So make sure that you have mastered u-substitution before you attempt some of these really, really tricky ones.